Hello and welcome to episode 1 of Rapid Research Reviews. I'm Robert, the Fascial nerd, and today I'll be talking about a paper titled Epimuscular Myofascial Force Transmission, a Historical Review and Implications for New Research. I have Nico here with me to make sure I keep my information straight. I wanted to start with building a foundation for the importance of fascia and why you might want to pay attention to the web-like network we all have just under our skin. This paper is a review of the literature available from January 2009. You can find the citation in the section below. The focus of the paper is on the force transmission in parallel to the myotendinous pathway. This form of transmission is the myofascial force transmission. This specific form is called epimuscular myofascial force transmission because it is the force transmitted outside of the muscle-tendon complex. This idea isn't a new one, though it has only recently gained popularity in helping explain the biomechanics of joint action. In 1732, Winslow suggested that we should look at the surrounding muscles, even if they were far away from the area, to explain complex motions. Almost 200 years later, Kronecker and Cash observed that muscles that weren't involved in a movement were shortened when nearby muscles were maximally contracted. They also observed that during intermediate contractions, the uninvolved muscle didn't shorten at all, likely showing the force dispersion effects of myofascial transmission. Denny Brown observed a force coupling effect when stimulating the tibial nerve, observing the soleus had a dampened contraction even though the tendon to the gastroc was severed. When the connective tissue from the gastroc to the soleus was severed, this effect went away. You might ask, if we've known of this effect for hundreds of years, why are we just now getting interested in it again? Well, sometime around the 1960s, anatomists in many places thought they had learned everything there was to know about the structures of the body, and just didn't think that fascia was that important in relation to the other tissues, due to lack of instruments available to scientifically measure the effects. So what about now? One study found differences in force between proximal and distal ends of a contracting muscle, showing that some force was instead transmitted elsewhere. Other studies have been done showing force transmission onto a bone that a muscle had no attachment to. In rats, they found that force is transmitted to all muscles and extramuscular tissue, including the antagonist muscles of opposing sides of a segment. A study in humans involved the flexor carpi ulnaris with a cut distal tendon. The wrist was put in maximal extension, which led to lengthening of the flexor carpi ulnaris, even though it no longer crossed the wrist joint. The lengthening was pretty severe at about 90% of the value of the intact version. When they stimulated the nerve, they saw shortening of the muscle. Finally, they removed the connection to the surrounding tissues, and almost all the effect went away. Another study done involving the flexor pollicis longus showed that 90% of subjects had an average of 5% force transmitted to their index finger, despite there being no intertendinous connections between the thumb and index finger's flexor tendons. This might have been the first in vivo experiment showing epimuscular myofascial force transmission. Lastly, in an elaborate study looking at the muscles in the limbs of cats, they found that a twitch to the medial gastroc also caused shortening of the fascicles of the soleus, possibly showing a mechanical connection between these two muscles. This is just the beginning of myofascial force transmission. I hope to talk more about that and discuss the clinical and rehabilitational implications in the future. Thank you for joining me.